Hi everyone, let us discuss this theorem. Okay, so in this theorem we have a power series summation n z to n, right? So for this power series, one capital R is defined. So that capital R is defined in this way: limit supremum of mod n raised to 1 by n. Okay, so in this way capital R is defined, and for this R we have three results or three conclusions. If mod z less than R, then given power series converges absolutely. If mod z greater than R, then given power series is divergent for that z, getting? And if you have any real number between 0 and capital R, then for this region given power series converges uniformly. Okay, so let us try to understand the geometrical meaning behind it. Okay, see, all of you are familiar with the standard form of power series. In previous video already we have seen, getting? N summation n z minus a raised to n, but see, a is not there, so that's why I simply wrote 0. Summation n z minus 0 raised to n, that means summation n z raised to n. So that means given power series is a power series about 0. Okay, so about 0. So R is defined in this way. So let me draw a circle with center 0 and radius capital R. Radius what? Capital R. Okay, if mod z less than R, so you know that mod z is equal to R. This is equation of circle with center 0 and radius R. Okay, what is given thing here? Less than R, that means interior part of circle. So if you take any point, okay, which is in interior part of this circle, then for that value of z, series converges absolutely. So if you take any point inside a circle, then for that point series converges absolutely. Mod z greater than R, that means outside this circle. So if you take any point z outside a circle, then for that value of z, series is divergent series. Okay, next, 0 less than R less than capital R. So that means if you take any real number which is less than small r, capital R, okay, which is less than capital R. So let me show it here. Now consider a circle with center 0 again and radius small r. Okay, obviously 0 less than small r less than capital R. Then mod z less than R. Mod z less than that R, that means inside a small circle. So if you take any point inside a small circle, then for that point what we have, series converges uniformly. Okay, so for that point given power series converges uniformly. Okay, so this is the result, this is the actual meaning of this result. Okay, let us prove this result. See, we will prove in three cases. First case, mod z less than R. Second case, mod z greater than R. And the third case, that small r lies between 0 and capital R. Okay, so make a screenshot of it, then we will go further. So let us prove the first part. What is the first case? We have mod z less than capital R. And what we have to prove? We have to prove that given power series converges absolutely. Okay, this thing we have to prove. So let us start with the given information. We have mod z less than capital R. See, we have two positive real numbers, mod z and R, getting? So definitely we can find a small positive real number small r which lies between these two. So let me write there. So therefore there exists some small r greater than 0 such that mod z less than small r less than capital R. So this is inequality number 1. After that, what will I do? I will take reciprocal of both sides. Okay, I am talking about this small r and capital R. I will take reciprocal. You know that when we take reciprocal, inequality will get changed. Getting? So that's why we will have, by taking reciprocal, 1 by r capital R less than 1 by small r. I am calling it as inequality number 2. So now let us focus on the definition of capital R. What is the definition of capital R? Let me write it here. Okay, we have, let me write, we have, what is the definition of capital R? Actually we define in this way, no, 1 by R. 1 by capital R is equal to limit supremum of mod n raised to 1 by n. See, it's a supremum, getting? It's a supremum. Limit supremum of this term mod n raised to 1 by n is 1 by capital R. Getting? So definitely by definition of limit supremum we can write, therefore there exists capital N belongs to set of natural number such that 1 by capital R greater than or equal to mod n raised to 1 by n for all n greater than or equal to capital N. As you can see here, limit supremum, it's a supremum value, so obviously it is greater than or equal to infinitely many terms. Okay, see, same thing we can write in this way, therefore mod n raised to 1 by n less than or equal to 1 by capital R for all n greater than or equal to capital N. Let me call it as inequality number 3, since 1 and 2 already we have got. So let us try to combine inequality number 2 and 3. Will you tell me what will you get from 2 and 3? Let me write here from 2 and 3. Let me what will you get? See, A less than B, B less than C. So definitely we can write A less than C. Okay, so therefore what can we write here? Mod n raised to 1 by n less than or equal to 1 by capital R and 1 by capital R strictly less than 1 by small r. So we can write here less than 1 by small r for all n greater than or equal to capital N. Tell me, can we take nth power of both sides? Yes, definitely. Let us take nth power of both sides. So if you take nth power, that 1 by n will get cancelled. Mod n less than 1 up by r raised to n for all n greater than or equal to capital N. Okay. So now let us multiply both sides by mod z raised to n. So when you take mod, definitely we will have non-negative values, so the inequality will be maintained. Okay, so what we are doing here, we are multiplying both sides by mod z raised to n. So let us multiply mod n mod z raised to n. Here also I am multiplying mod z raised to n by r raised to n for all n greater than or equal to capital N. So you are familiar with this property of modulus, that is mod z1 into z2 is equal to mod z1 into mod z2. We can take separate mod. Okay, so if you use this property here, definitely we can write at both sides. In both sides I am using it, mod n z raised to n, this is less than mod z raised to n, and here r raised to n. So we can write mod z by r whole raised to n for all n greater than or equal to capital N, right? So this is a very important thing we have got. Let me call it as 4, inequality number 4. See, but let me write but summation n running from, what we have, n running from 1 to infinity mod z by r raised to n is a geometric series, So I hope all of you are familiar with a geometric series. In a geometric series we have a first term and common ratio. Actually that series in a form ar plus ar square plus ar cube, in that way, getting? So that means we have one term, we multiply each term by some fixed constant, so we get a next term. So in this series we are having the same thing. So it's a geometric series with a common ratio, with common ratio. What is a common ratio here? Mod z by r. Okay, since in this series if you expand, you can easily see if you multiply each term by mod z by r, you will have the next term. So that's why it's a geometric series with common ratio, this one. But do you remember one thing, that mod z is less than r. Okay, so see what we have, mod z is less than r. So if I shift small r on this side, so mod z by r less than 1. So what I want to say, this is common ratio mod z by r which is less than 1. See, and already we are familiar with that result. If you have any geometric series with common ratio less than 1, then 101% it is a convergent series. So this is a geometric series with common ratio less than 1. So definitely what can we say? It's a convergent series. Okay, make a screenshot of it first, then we will go further. So therefore I have written summation mod z by r raised to n is a convergent series. This is our conclusion. But did you notice this mod n z raised to n is less than mod z by r raised to n? Getting? So see, this series is convergent and this mod is less than that. So definitely by comparison test we can say this is also a convergent series. Getting? So that means what we get here, If larger series is convergent, definitely the smaller series is convergent. Okay, so therefore let me mention here. So therefore from 4 and by comparison test, what can we write? Summation mod n z raised to n is convergent series. We are calling it as convergent series, but see, we have a mod here. So therefore what can we say? We can say this is absolutely convergent series since mod is there. So therefore summation n z raised to n is absolutely convergent series, you can easily see series converges absolutely. So this thing we have proved here. So let us go for the next case. Make a screenshot of it first, then we will go further. Let us discuss third case first and then we will go for the second case. Okay, so what is the third case? Third case is 0 less than small r less than capital R. Then the given power series converges uniformly for that domain. Okay, so let us start with the given condition. What we have, let me write it here. We have 0 less than r less than capital R, right? So again I will use the same technique which we have already used for the previous case. So that means if you have two positive real numbers, small r and capital R, then definitely we can find some positive real number which lies between these two. Okay, so let us take gamma greater than 0 be such that r less than gamma less than capital R, right? Okay, see, actually rho greater than 0 such that r less than rho less than r. Okay, so let us call it as yes, this is inequality number 5. Okay, see, now what will we do? I will take reciprocal of both sides. So you know that when we have inequality, if you take reciprocal, inequality will get change. Okay, so therefore what can we write? So therefore 1 by capital R less than 1 by rho. This is inequality number 6. So let us follow the definition of capital R again. Okay, what is definition of capital R? Let me write it here. We have, tell me, what is the definition of capital R? 1 by capital R is equal to, this definition is given in a statement of theorem, limit supremum mod n raised to 1 by n. Okay, again I will apply the same logic. Again I am going to use the definition of limit supremum. So by that definition we can write, therefore there exists n belongs to set of natural number such that 1 by capital R is greater than or equal to mod n raised to 1 by n for all n greater than or equal to capital N. So as the definition says, it's a limit supremum. So it's a supremum, it's a maximum value. So definitely it is greater than or equal to infinitely many terms. Okay, so this is a very important thing we have got. Same thing we can write in this way also. Therefore mod n raised to 1 by n less than or equal to 1 by capital R for all n greater than or equal to capital N. So let us write the remaining part here. I am calling it as inequality number 7. So let us combine 6 and 7. See, A less than B, B less than C. So definitely we can write A less than C. So yes, from 6 and 7 what can we write? Mod n raised to 1 by n less than 1 by rho for all n greater than or equal to capital N. Okay, so can you guess the next step? Yes, same thing I am going to do. Let us take nth power of both sides. So if you take nth power on this side, that 1 by n raised to 1 by n will vanish and you will have simply mod n less than, on this side you will have rho raised to n for all n greater than or equal to capital N. So let us multiply both sides by mod z raised to n. Okay, so mod z raised to n. See, it's a non-negative number. So if you multiply both sides, so you will have the same inequality. That inequality will be maintained. So mod z raised to n, okay, on this side also, less than mod z raised to n by rho raised to n for all n greater than or equal to capital N. Okay, so now what will I do? See, you know that, let me write it again. So yes, mod z1 into z2 is equal to mod z1 into mod z2. So by using this property of mod, I can write mod n z raised to n less than mod z by rho raised to n. But yes, I should carry this inequality for all n greater than or equal to capital N. Okay. But see, mod z we have written somewhere. Yes, they have given mod z less than r. This is the given part. But mod z less than r. Okay. I should mention given. So that means for this domain, particular for this domain we are discussing. So let us use this inequality here. So what can we write? Mod n z raised to n less than mod z by rho raised to n less than, see, mod z is less than r, so r by rho raised to n should carry this in condition, mod n greater or equal to capital N. So a less than b, b less than c, so a less than c. So what can we write? Mod n z raised to n less than r by rho raised to n for all n greater than or equal to capital N. Very important thing we have got, let me call it as 8. Okay, let me call it as 8. See, there is no more space to write, make a screenshot of it, then we will go further. But please keep this thing in mind, r is less than rho, since we are going to use it later. Okay, make a screenshot of it, then we will go further. See, but let me write it here. But summation r by rho raised to n, running from 1 to infinity, is a geometric series. So we are already familiar with a geometric series. Geometric series, that means we have a first term and we multiply each term by one perfect constant, then we get a next term. So if you expand it, definitely you can say it's a geometric series with a common ratio. Its common ratio is, let me mention, series with common ratio. What is its common ratio? R by rho. But see, it is definitely less than 1. So reason is, since our r is less than rho, you can go back and you can check this inequality we have already mentioned there. I think inequality number 5 or 6. So r is less than rho. So that's why if you shift rho on this side, so we'll have r by rho less than 1. Okay, so this thing we get there. So this is a geometric series with common ratio less than 1. So we have very standard theorems. If you have geometric series with common ratio less than 1, then 101% it's a convergent series. Okay, and if it is greater than 1, it's a divergent series. So we have a geometric series with common ratio less than 1. So that's why we say it's a convergent series. So therefore summation r by rho raised to n is convergent series. It's a convergent series. See, this series is convergent and mod of n z raised to n is less than that. So that's why what can we say? You remember that Weierstrass M test? It's a constant r by rho. Okay, so Weierstrass M test says if you have, let me mention it here. If you have mod z less than, or so suppose we have mod a n z raised to n less than mn. Okay, mn, where mn is greater than or equal to 0. Mn is greater than 0. And if summation mn is convergent series, then summation n z raised to n is uniformly convergent series. Okay, so by what? Weierstrass M test. So here I am also going to do the same. At a place of mn, we have got this r by rho. Okay, r by rho. So it's a r by rho raised to n. It's a convergent series. So therefore, by, let me mention here, Weierstrass M test. What can we say? The Weierstrass M test, summation a n z raised to n is uniformly convergent series. Okay, it's uniformly convergent series for mod z less than r. I should carry this condition. We have used it there, getting na? So that's why I should carry this condition. So therefore, if this series is convergent, we have already proved, since it is geometric series with common ratio less than r, and it is less than that one. So therefore, by Weierstrass M test, definitely we can say the given series is uniformly convergent, but for this domain. Okay, so in this way we proved second case also. Okay, so let us see, in this way we proved third case here. Okay, so let us go for the second case now. Make a screenshot of it, then we will go further. So let us discuss second case. Okay, mod z greater than r, then we have to prove the series is divergent series. Okay, so let us start with a given condition. So we have, okay, what we have, mod z greater than capital R. So definitely we can find a small positive real number which lies between this mod z and capital R. So therefore there exists R greater than 0 such that mod z greater than R greater than capital R. Okay, I am calling it as I think inequality number 8. I do not remember exactly, but it's 8. Let us take reciprocal of both sides. So what will happen if you take reciprocal, inequality will get changed and you will have 1 by R is greater than 1 by small r. This is inequality number 9. Okay, so let us go back to the definition of capital R. What is definition of capital R? Let me write it here. We have, what is the definition of capital R? 1 by capital R is equal to limit supremum of mod n raised to 1 by n. See, it's a supremum. It's a supremum, and this 1 by small r is less than that. 1 by small r is less than that. It's a less than supremum. So therefore we can write. So therefore by definition of limit supremum, what can we write? 1 by r is less than or equal to mod n raised to 1 by n for infinitely many n. Okay, this is true for infinitely many n. See, actually it's a supremum and we have a 1 by small r. It's less than that. It's less than supremum. So that's why we get this type of inequality. After that, let us do the same. Let us take n power of both sides. So we'll have 1 upon r raised to n less than or equal to mod n, again for infinitely many n. Let us continue it here. Let us multiply both sides by mod z raised to n. So what will we have? Mod z raised to n r raised to n is less than or equal to mod an mod z raised to n. So we can write this one since in previous cases we have already done. Okay, so let me write it here for infinitely many n. So therefore mod z by r raised to n is less than or equal to mod n. Okay, I should write here z raised to n. Okay, and again it is true for this is true for infinitely many n. Okay, see, but summation mod z by r is geometric series with common ratio. Will you tell me what will be the common ratio? Mod z by r. Okay, I should write here raised to n. So it's a geometric series. Same things. Already in previous cases we have done the same. It's a geometric series with a common ratio mod z by r. Tell me, it is greater than 1 or less than 1? Will you tell me? Shall we use this inequality number 8? Mod z greater than r. So mod z by r is greater than 1. So let me write the reason here. Since mod z is greater than r, so if you shift r on this side, so mod z by r greater than 1. So it's a geometric series with common ratio greater than 1. Already I have told you, when you have a geometric series with common ratio less than 1, then it is a convergent series, and when we have a geometric series with common ratio greater than 1, then it is a divergent series. So therefore summation mod z by r raised to n is divergent series. Okay, it's a divergent series, and see, this is greater than that. This is greater than that. That means 100% it's a divergent series since it is greater than that. So therefore summation an z raised to n is divergent series. Again, by comparison test we can write it's a divergent series. So in this way we proved the given series is divergent series. Okay, so we have completed the proof of all three cases. So after that we are going to discuss one statement of theorem. Okay, statement of one theorem which is generalization of this result. Okay, make a screenshot of it first, then we will go further. So now note down the statement of this theorem. This theorem is same as the previous one. Simply, for previous theorem we had a power series about 0, but for this theorem we have a power series about a. Okay, so let me make one rectification here. So here I should write mod z minus a less than r. Okay, small r. See, statement is same. At a place of z we have z minus a everywhere. Okay, so it's a theorem generalization of previous one. This theorem is so much useful for solving problems. Okay, so please note down this theorem. After that we will stop. Thank you. Bye bye.